So we'll finish off today's lecture with an example from an old game show called the Monty Hall Show, I think. It's before my time, I don't know. And the problem goes like this. So you're on the game show, there are 3 doors. Behind one of the doors is a new car, and behind the other 2 doors are goats. Now, if you pick the door with a car, you win a new car. If you pick the door with the goats, I guess you win a goat. The way the game works, though, is kind of interesting. So you've got the 3 doors, you make a guess. So for example, I'm going to guess door number 2. The host of the show, who knows what is behind each door, doesn't immediately open door 2 and show you what's behind it. No, the host opens one of the doors that contains a goat and shows you that a goat is behind that door. So for instance, I selected door 2. It could contain a car, could contain a goat, I don't know. The host knows. The host says, oh, I know that a goat's behind door number 3. I'll open that up, show you there's a goat behind there. And then the interesting thing is, after showing you that door 3 had a goat, Monty would ask you, do you want to switch your door? Do you want to switch it from 2 to door 1? Seems kind of strange. Why would they even ask that? Okay. So the question is, I have 2 options here. I either stick with door 2 or I switch to door 1. Which do I pick? So think about it for a second. You originally selected door 2. Door 3 has a goat behind it. What do? Do you keep with door number 2 because it has just a higher chance of winning as door number 1? Or do you switch to door number 1 because it has a higher chance of winning than door 2? Okay, so you can think about it for a second, but I'm going to move on to answer this question with the simulation. What we're going to do is we're going to calculate the probability of winning if we switch and the probability of winning if we stay, which is just 1 minus the probability of winning if we switch. So I can just focus on calculating this probability, the probability of winning if we switch doors. Whichever strategy has the higher probability of winning is the right or the better strategy to use. Okay, how do we calculate these probabilities? I'm going to simulate. I'm going to simulate the problem many times to estimate the probabilities. So first, I want to figure out how do I simulate one game of Monty Hall, then play a bunch of games, and then count the proportion of wins for each strategy. All right, let's do it. How do I simulate a single game? So when a contestant picks their door, there are 3 equally likely outcomes. They could either see goat number 1 behind that door, goat number 2 behind the door, or the car is behind that door. So let's make a random choice of what is behind the door that the contestant picked. Car, goat 1, or goat 2. Okay, so for example, in this random simulation, what was behind the door that I picked was goat 1. This is the first door that I pick, right? That I originally picked. That's what I mean by the door. Okay, so suppose we can see what is behind their door. I mean, the contestant can't, but we're the host of the show, so we can see. So if it's a car, then the winning strategy is to stay. But if it's a goat, the winning strategy is to switch. It's as simple as that. If it's a car, stay. If it's a goat, switch, and you will win. So let's write some code to figure out the result of each strategy, or what the winning strategy is. So if what was behind the door was a car, then the winning strategy is to stay. Otherwise, if what was behind the door was a goat, then Monty will reveal the other goat, and if I switch, I win the car. So here's my code. It calculates the winning strategy. So I'm going to throw that into a function. Okay, so the function will take a random choice from this to figure out what is actually behind the door that I picked. Then we'll say, okay, if what was behind was a car, you should stay. Otherwise, you should switch. And then it'll print out the winning strategy, and it'll return the winning strategy. So define the function. Let's run it. It says goat 1 was behind the door, so you should switch. And it returned switch as the winning strategy. Okay, if I run this over and over again, it says car was behind the door, you should stay. Okay, goat 2 was behind the door, you should switch, and so forth. So I'm going to run this simulation a bunch of times and see which is the most common strategy. So I'll run it 100 times here. Simulate Monty Hall 100 times. I'm not saving the result, you notice, I'm just printing out the results. And you see I get a lot of switches. which suggests that it might be the best strategy. And in fact, turns out that it is. So let's use our recipe here to save the results into a variable, into an array. So I'm going to run this 10,000 times now. I will set winning strategies to an empty array, iterate 10,000 times, run my simulation, save it into winning strategy, and then save that back into the array winning strategies using numpy append. Remember that numpy append creates a new array, so I have to save it back here like this. Okay, so I run this, and I get 10,000 results. So it's taking a second. Actually, most of what's causing this to be slow, taking a second, is the print. So if I went back and I got rid of the print from the function, okay, then this should be much faster. Maybe not much faster. It should be faster though. Okay. In general, you want to avoid printing whenever you're iterating like 10,000 times because you're just displaying a lot of information to the screen and it takes time to do that. All right, so I have an array now, winning strategies, with the winning strategy of each simulation, all 10,000 of them. So how many of them, in how many cases, in how many instances was the winning strategy to switch? So I will use count non-zero to count the number of times that the winning strategy was switch. And in this case, it was 6,666. And then the proportion of times that this was the case was 0.6666. We got incredibly lucky here because it turns out the exact answer is 2/3. And so 0.6666 is accurate to 4 decimal places, which is awesome. But if we were to do this again, we would see something close to 0.6666, but not exactly. 6565 in this case. So that tells us that the winning strategy is to switch, right? Because the probability of winning if you switch is 2/3. The probability of winning if you don't switch, if you stay, is just 1/3. Okay. Now I know that it's 2/3 and 1/3 because I know about the problem, but if we just ran the simulation, we would get 0.6565. We wouldn't be able to immediately guess that it's 2/3. You might say that, hey, this looks close to 2/3. It's probably 2/3. There are 2 remaining doors. There are 3 total doors, so 2 and 3 seem to be likely numbers to use in computing the probability. But we don't know that it's 2/3. We'll just say, okay, it's 65%. That's more than 50%, right? The probability of winning if you stay is 1 minus this. And so we'd say, okay, this looks like to be the winning strategy, or the most probable, the strategy that is most likely to win. Okay, we're not guaranteed to win if we switch, but we are more likely to win. So this is a famous problem. I like this story that kind of captures the incredulity of people whenever they hear that this is the right answer. So there's this person, Marilyn Vos-Savant, who was, I guess, a savant, kind of like, one of the people who's known to have a very high IQ. She had a column in Parade magazine. Somebody wrote in and asked this question, and she stated the correct answer. You should switch. She received over 10,000 letters in disagreement. Some of them, a good percentage, 1,000 letters from people with PhDs who said, no, the right answer is to stay, or it doesn't matter, the probabilities are the same, and she was right. So this is kind of a unfortunate example of people needing to prove that they know more than someone with demonstrably a very high IQ. So in summary, what we did here was we made a function that runs the experiment once, we ran that function a bunch of times with a for loop, and then to calculate or to approximate the probabilities, we used numpy count non-zero. So that's sort of the formula, that's sort of the recipe that we're going to be using over and over and over again in the rest of the quarter to calculate probabilities. It's as simple as this. Sometimes actually running the experiment once is what takes more thought, is a little bit harder, but the basic idea is exactly this. Okay, so I think next time or the time after, we're going to go back to that problem at the beginning of lecture, the Swain versus the state of Alabama case, and take a look and see, is the Supreme Court at all right that this could be due to chance, or are they totally off base? I'll give you a hint. Yeah, it's not due to chance. Okay, I'll see you all next time.